Okay, we are good to go. Hopefully people can see my screen this time. Yes.
Yes, sir.
Okay, perfect. All right. So let's start today with the next set of architectures that are pretty interesting in modern AI and deep learning literature are recurrent neural networks. I don't know why I named them CNNs. Apologies. RNNs. Okay, so I kind of subtitled this AI down the memory lane. So people try to model human-like memory. It's very interesting because memory has interesting properties, right? You are able to maintain information for a period of time so as to do something with it. And it was interesting to explore that there are possibly network architectures that can help us perform um, things that are requiring some amount of information to be kept in temporary storage, and that people knew for a long period of time. But why did first recurrent neural networks emerge? And to answer that question, we need to see the idea behind sequences. So anybody can tell me what are actually sequences? What do sequences mean? What are they? Anybody wants to give a go?
They are a kind of list of objects, you can say, which
Yeah,
have dependency on the previous object. Like each
exactly.
dependency below has some kind of a dependency on the previous one.
Perfect, perfect. So in some sense, they have what's called some temporal autocorrelation or a temporal order in them, right? Like these are data that have temporal order in them. So if I take a time series data, right? I have some time series data, right? Like some data varying across time. The idea is that if I pick a specific window of that and then I pick a window that's slightly previous to it, there is some structure in these, right? That's the idea of the temporal autocorrelation. So such data are important to understand because there is a lot of real world data that have temporal structure in them. Can anybody give me some examples of real world data that have temporal order?
Stock market data.
Yeah, stock market, pretty much. Yes. So that's there's some history dependence there.
Video
Any
frame.
sorry, video, yeah, video, right? Stock market,
NLP.
videos, right?
NLP.
I mean, those are methods, right?
Sales data.
Yeah, sales data has it. Yes.
Any
Sentences
story,
also. Sorry.
story, any
Yeah,
story, movie story.
movies,
Speech.
stories. Those are also in parts, in some part, videos, right? Stories.
Speech.
Text stories
Ah,
also can be.
yes. Speech, language. Instead of saying speech, I would say language. Language has some structure, right? Temporal correlation. Sorry. Yeah, language. Anything else that you can think of? Yeah. So pretty much you guys named it, right? Like these are the things where there is a temporal order to it. I'll give you some examples. First is language, right? So, for instance, if I say a sentence, an apple a day keeps the, right? And you know what's coming up next, right? And how do you know that, right? Like then there is a temporal order in which this sentence is placed so as to predict what's going to come up, right? Now, if I jumble this order, it does not make sense, right? So that means that this sentence in this order gives rise to the next two words in this sentence, which is the doctor away, right? So the point is that this temporal order is very important to predict what is going to come next, right? So in some sense, language or whatever we speak and communicate has temporal correlation structure in it. And to give you some other example, music has a very nice underlying structure, right? Like for example, notes in a specific rag or ragam, right? If you have like a specific set of notes and then you sing a specific rag, and then you know what note will likely follow a specific sets of note, right? So that is another way in which temporal order is preserved. in such.
What is meaning of temporal? Means what?
Temporal order is this: if this is across time, right, that means that there is some dependency of the sequence to the previous things that are happening in the sequence. That's temporal. Temporal means time.
मतलब पिछले समय का impact, right?
पिछले समय का impact, exactly. जो पिछले समय में हो रहा है उसका impact जो next step में हो रहा है उसको temporal बोलते हैं. Okay, so the point is whatever is happening in the past is dictating whatever is happening in the present in some sense, right? There is some structure in there. That's what I told you. If I take a small window of, you know, some capital T and I just shift it slightly to T minus tau, right? Then the data that is present here and here has some correlation to it. Okay, and that information is something that sequences have. And how do we exploit that in order to do some prediction? Because there's a lot of real world data, as you mentioned, right, where predicting the next step or understanding the patterns in the sequences becomes a very important thing, right?
This means like before delta t time,
Mhm.
whatever event will happen, that impact will happen after delta t time or at t time.
As in the point is what is happening is T minus tau has some relationship to what is going to happen at time T, right? So that relationship is preserved in this data. Okay, now we have to exploit this structure in order to do some predictions. Like for instance, when I said an apple a day keeps the immediately the thing that comes to your mind would be the doctor away, right? Now how can a machine do this, right? How does it understand this context that this is going to predict these two words next, right? And for example, in a music, if it is a set of rag, so if I sing some notes in a set of rag like ni re ga or something like that, what is the next note in that rag, for instance? So that is predicted by what is coming before and the current context in which these are being sung at. Okay. And often there is also real world data from physiological signals like body signals, right? For example, I'm a neuroscientist. I like to study the data from the brain, from the heart, from muscles, and so on. They are also, in some sense, time series data, like, for example, the electrical activity of the brain, heart, because if you know the method like EEG, where they place sensors on top of the head, if this is the head, right? Top of the head, they place some sensors and you can record from the sensors some amount of information, and then that has some temporal structure to it, right? Like what is happening at window time T minus tau is going to predict what is going to happen a little bit later, right? So all these are time series data in some sense, right? They are data that is going across time, and they have some underlying structure to them. And our aim is to exploit this structure to do certain computational tasks, be it prediction, classification, transformation, so on. Many things. And we'll talk about some of the examples though. But hopefully this is clear. So the idea of sequence learning comes from these, these real world data. That is, if you consider the following problem scenario, let's say I have information about the temperature of a reactor across time, right? And then I collect some data points and I see that the temperature is increasing. Now, if I have to make a prediction about the next point in the sequence, what would the prediction be, right? Would it be something like that or something like this, right? Now, how does this next point be determined? How can you predict this next point, right? That means that you need to have some history of how the temperature varies across time. Use that information to predict what is going to happen in the next point. Okay. Now, to give you an example from another thing like language, if I say the pen was filled with, right? There could be two options here. The next word in the sequence could be something like blue ink, right? Or I can say fluffy sheep. Now, based upon what was the context of what the pen meant, right? In the first context, the pen meant it's a writing pen, right? In the second context, the pen is a sort of like what's that? An area where sheep are basically, housed. That's also called a pen, right? Or livestock is housed. So in that case, the context matters, right? The context dictates meaning. So in some sense, the understanding of this entire sentence comes from the fact that you understand what pen means and so on, right? And that's how you are able to understand the entire sentence. And so this temporal structure is context dependent, right? Like what it currently means, that is very important. So what do RNNs essentially do then, right? Then what's the concept and what's the point behind using recurrent neural networks is essentially it's able to predict future, performing prediction of the future. That is, if I give it a set of data, right, which is in a sequence, right, can I predict what is going to come up next? Okay, that's number one. And second thing, classification of a sequence. For instance, if I give it a certain pattern of data, like for example, the pen was filled with sheep, then if I ask it a query, what is the meaning of pen here, it needs to understand that the pen here is different from when I say what the pen was filled with blue ink in that case, right? So the context dictates what the meaning is, the sequence dictates the meaning. So that way it has to understand what the entire context is. And in case of prediction, it has to understand patterns in the sequence and then use that information to see what likely the next point in the sequence is. Right? Any questions here? Right? So that's the idea of sequence learning. Right? You want to do sequence learning, and how does that work? We'll have a look at what the architecture of RNNs is to exploit this temporal structure in the data. Right? So that's the idea behind RNNs. Okay, hopefully everyone is on board, on the same page, and we can look at the next step where we are looking at the architectures of RNN, because let's dive into it, because the architecture tells you a lot about what purpose the RNN actually tries and solves, right? So some of the examples that we gave before. So like feed-forward networks, like CNNs, like CNNs, RNNs are just a simple extension of the feed-forward networks. It's just that they are arranged in a specific way in order to exploit certain aspects of the data structure. Okay, so this typically start as extensions of feed-forward networks. So that means a feed-forward network. Typically, we would lay down a feed-forward network horizontally, but we would typically this would be vertically aligned. Most of the papers that you would see, or literature, or even sources online that you would see for the RNN architecture, places them horizontally. If someone's trying to join, then join in like the IIT email ID, or if I have to, is our TA here somewhere? No? Okay. So if the TA is there, they can let them in, but join with the IIT ID. Just let your colleague, your classmates know about that. So let's talk about this, right? Now, what's difference in the RNN architecture here, right? What is the difference? The difference is here, right? That is, there are connections within the hidden layer, right? Which is often the reason why the word recurrent comes from. That is, there is recurrence in the hidden layer. That is, the hidden layer activations are recurring across time. Okay. And that is the entire reason why the word recurrent neural network comes. That means that the hidden network or the hidden layer activations or the hidden layers representations are repeated across time. They are recurring. And that information is able to hold some of the history of the sequence in order to make decisions based upon that history. Okay. Now, when you see an RNN figure like this, it's typically laid out more like this, Okay, so let me explain what's happening, right? So you have our input so this is what is happening across time. So time is flowing forward like this, right? And at each time step, you have an input that's going into the system, for example, X naught. And there are certain weights that transform the input into the hidden layer, right? Hidden layer H naught. And then that with some other weights W out transform into the output, okay? But across time, something is also moving forward. That is, the hidden layer activations through the weights W hidden, right, are going from one time step to another. That is, these are recurring across time, right? And those are getting pushed forward through time via these weights W hidden. And when the next time step comes, the next input enters into the system, right? And then that activates the hidden layers, which is a function of both the inputs and the previous hidden layer activations, which then produces the output. Then again goes on and goes like this as time progresses. Okay, so at a given time point, the input to a RNN is two things. One is the current input, right? Whatever input is being fed in, and the previous hidden layer, right? That is H of t minus 1. Okay, if I consider this to be time equals 1, right? Let's say. So at time equals 1, x1 goes in, the hidden layer activations get computed, and the previous hidden layer information also comes in to that, right? And this is why you have some preservation of history, because in these hidden layers, activations are a representation of information from the past. Okay.
So what the word recurrence, where it is actually impacted?
The recurrence is this part, right? That is, the hidden layer is pushed through, correct, through each of
भी चीजें बार बार यूज की जा रही
हाँ
हैं.
बार बार यूज की जा रही है, और ये चीज हमेशा ट्रांसफॉर्म होके फिर से हिडन लेयर में जा रही है. So that's the idea behind recurrence. ठीक है. So the point is, the hidden layer activations are taken across time. So there is some part of the previous inputs representation that is preserved in this hidden layer, और वो बार बार नेक्स्ट लेयर पे जा रहे हैं,
पुराने मुद्दे बार बार हाईलाइट किए जा रहे हैं,
हाईलाइट किए जा रहे हैं. Exactly. So that's the idea behind this, the recurrence. So this is where the recurrence is happening. Right? Okay. Recurrence is reoccurrence. That's the formulation of the word.
So the length of the recurrence will be the length of my number of hidden layers, right?
So yeah, we will discuss that. I'll tell you about that. But yes, so it will be transformed using the hidden layer weights. But we'll discuss the dimensionality and everything in a couple of slides. That'll be very clear. Yeah, we'll do that. Okay. But let you. Yes.
Sorry, just one question.
Sure. Of course.
At the end of it, it is one network only, right?
It's just one network. Yeah.
So,
it's not many networks. This is through time. That's what I mentioned, right? So this is happening across time.
So every hidden layer has the input and an output.
Right. And the input is coming from two things. One is the input that you are feeding in. So let's say the input that you are feeding in could be some words in a sentence, right? So for example, or let's take that sentence, an apple, and so on and so forth, right? So you're feeding this input to this hidden layer, right? And then hidden layer activations are getting also inputted into the next time step, right? Which is where the recurrence happens, and it goes across time. And then at the end of the day, you are trying to make a prediction, right? In this case, at every time step, you're taking an output, but there are many variations of recurrent neural networks, which we'll look at, right?
Then, sir, what is the difference between this architecture as well as decoder, encoder, or transformer?
So for instance, this architecture, the hidden layers, if you imagine, right, the hidden layers are getting sent from one time step to another. In those architectures, if I don't have this recurrence, every time you send in an input, the hidden layer is overwritten, right? There is no information about the history, right? So this is not there, right? Every time I get an input, I'll get the hidden layer activations based on the input. There'll be nothing about the past that is preserved. I see. So that's the special thing about the recurrent neural networks. That is, there's something about the past information that is also there in the current present information.
Sir, one question. So we do the back propagation for every step, correct? So we send x0 and I do calculate something and back propagate to configure this W. So here you are saying we are preserving that. So is there a back propagation that will also happen?
Yeah, we look at it. It's called back propagation through time. So instead of now doing it for every step, you do it across time. It's called BPTT, back propagation through time. Okay. We'll look at it. We'll look at least I won't look at it, the entire mechanics, but I'll tell you the concept because the math is exactly the same. So instead of propagating the errors across just one instance, you would propagate the errors across time, right? And that is why RNNs are slightly harder to train, because longer the sequence, the longer you would have to back propagate the errors, and there you have more issues of the vanishing and exploding gradients and all that, right? So those issues come. We will discuss everything. But
okay. And one more question, sir. This is what you are saying. This is for during the training phase, correct? Not the final output. Or
no,
is it the
no. This is just the architecture. I'm not even going. This is what I would say is the forward pass for a recurrent network, right? Like we are just sending in inputs, getting outputs from it, right? And how the dynamics changes across time is what we are discussing right now. There's nothing more than that. Okay. All right.
Sir,
So
one question.
yeah, of course.
This W input and W output and W hidden, is it same across all the
Very good. It is same across all the inputs. So that was my next point I was about to make. Yes, the W input stays the same, except for when they are being trained by learning. The weights hidden also stay the same. The weights out also stay the same. That's very important to understand, because these do not change. Only the activations change across time. Okay. And as you learn, these weights get trained to minimize certain loss that you are actually trying to make the network achieve to do. And that will change the weights, but these weights are not changing across time. The activations will change based upon your input and the previous hidden layer output. Okay. So if that is clear for everyone.
Sir, but when you are passing W hidden from H1 after H0, it will have some transformation, right?
It'll be the same. I'm saying that this won't change. This will be the same as what it is here. But depending upon your input and the previous hidden layer activations, the next hidden layer activations will get influenced. Is what I'm saying. Okay. Yeah. The values will not change if you have frozen the training. For example, once you have trained this network, this will not change. Okay, this won't change.
Sir, one question.
Of course.
So the length of input layer, it can change, right?
That can change, depends on the time of the sequence length, right? That is, if this is a longer sentence, then this would be if you unwrap the recurrent neural network, that will be a longer.
So does it mean that for different length of sentences, same neural network won't?
Yeah, very good question. So these are the things that we'll answer today. Okay. Yes, you are thinking in the right direction. People are all sort of thinking about it correctly. That means that the length of the sequence matters, how much amount of past you can remember also matters, and all that. Right? It is very crucial and critical, and that's where we look at certain extensions of recurrent neural networks. We look at both graded recurrent units, GRUs, and LSTMs, long short-term memory. Okay, so we'll look at both of them. Okay, everybody on board? Cool. All right. So So I'll erase this part for now. But the idea is that I can represent a hidden layer activation by, there's a nonlinear transformation or an activation function f, but it is a function of the previous hidden layer output transformed via some hidden layer weights plus your current input xi. Okay. So at every time step, you get this and this. So both of them combine to form the current hidden layer, which then gives you your output. Okay. And the output is very simple. It's again a nonlinear transformation where, sorry, this must be out. Okay. Apologies. No, it's not hid. That's out. Okay. W out into HI. Okay. So W out into HI will give you YI. Okay. So typically in RNN literature, the activation functions are tanh. The reason they are tanh is because tanh spans from -1 to +1, right? The range. And these act as really good representation of activations in the hidden layers. Okay. So most often than not, as practice, tanh is what is used as an activation function in your hidden layer representations. Okay. So just a side note there. Okay, but the formula is pretty straightforward, right? So you have the hidden layer activations, which is a weighted sum of the previous hidden layer and the current input, and the output is taken as certain another projection of the hidden layer activations onto the weights output, and then taking a nonlinear transformation of that. Okay. Now, what people have done is they have seen that specific ways in which you can arrange recurrent neural networks that will give rise to certain types of functionalities. Okay. So for example, if I place the hidden network like this, where at every hidden layer, I take the output, this can be used for things like machine translation, right? For example, the police captured something like that. If I give a sentence and I want it to be translated into, say, something like Hindi or Spanish or whatever language it is, right? So how does this happen? So at every time point, we need like an output. So that way, this sort of an architecture can be utilized for doing machine translation, for instance. Okay. But there are certain modifications to this architecture. For example, something like this, right? So instead of taking the output at every time step, if you send in input sequences x1, x2, x3, and then take in an output at the end of the sequence, for example, what likely could be the applications for this? Any idea? Anybody?
Aggregators.
Sorry?
Kind of
Translation.
Translation could be one, but previous one is a little bit more amenable to that.
aggregators.
What would you, I mean, if you think about it in the same language context, what would why would you design such an architecture? What do you want from it?
Getting the context of what was
sentence means, right? Like for instance, language prediction. Right?
Yes.
So you give it a sequence of sentences and you predict what the language is, whether it was English, Hindi, Bangla, or Tamil, or whatever it is, right? So how does that happen, right? So that can be exploited by using such an architecture.
And sir, syntaxical analysis also we can do by this, right?
There can be many applications for it. I'm just giving you some examples. But where you want to predict one output at the end of a sequence, right? There can be numerous such applications, right? For such a thing. But yes, of course. Yeah. So there are other interesting architectures in this, which I would also urge you to slightly dig deep into, where it looks like this, right? The previous hidden layer outputs, instead of going to the output, comes as input to the next hidden layer, to the next part of the sequence, right? So it comes out and goes into as your input. So this is your output, which goes as input again, which is your output that goes as input again. And then finally, you take an output. what would likely this be used for? Any idea?
Yeah, so note music creation. One
Very
single
nice.
note you will provide.
Oh,
It will
superb.
give you the song
Yeah,
or a
yeah.
story creation.
Very nice, very nice. Yeah,
Paragraph
yeah,
you will give. It will
yeah.
give.
I just you put that. You just read my mind there. Yeah. So generative music, right? Like imagine nowadays there are these copyright issues, right, with music that you put on YouTube, or if you have a channel, you are always worried about copyright strikes. So you want some music that is out there which probably can be generated and that does not have overlaps or significant overlaps with current music. And this could be one way of doing it. Absolutely, right? You give one note and then this then. So that means that this network has to be trained on certain types of music, and then you give it a sequence of notes initially, and then that generates music at the end, basically, right? Like that tells you the next sequences of outputs. So that's an interesting way of organizing the RNN architecture to exploit the underlying sequences or sequential temporal correlation data, correlation sequences in the data, right? Exploiting the temporal autocorrelation structure. Now, one question here is, and at least one point to note in the architecture as such is that the inputs, hidden layers and output can have many dimensions, right? This can be many units, this can be many units. For example, the input, depending upon the type how you encode your input sequence, right? There are many types of encodings and embeddings that you can use. Let's say my input is 10 dimensional, okay? And I'm saying that the hidden units can also have many many hidden layer can also have many units, and let's say this is 20 units, for instance, okay, and the output is say 3 units, okay. Now with this idea, can anybody tell me what the dimensionality of the inputs would be, weights of the inputs would be? Wn. So if I had to take a 10-dimensional input and convert it into a 20-dimensional, so that means that there are 10 nodes here.
One row of 10.
And then here there are 20. So what is the way in which you will transform 10 to
10 cross
20?
1 input.
10 cross 1 input, yes, 10 cross 1. But what is the dimensionality of these weights input?
10 cross 20.
Yeah, 10 cross 20 or 20 cross 10, whatever. 10 cross 20, right? Let's put it as 10 cross 20. That's much more appropriate, because you do W transpose X where there is
Yeah.
10 cross 20.
For
Okay.
every 10 there is a 20 hidden, right?
So so there are 20 hidden layers. So what will be the dimensionality of hidden weights hidden?
20 cross 1.
Think
1
again.
cross 20.
1 cross 20.
No. That's the tricky part. Okay, so let's first do output. What will be W out?
2 cross 1.
No, there are 20 hidden
20
units.
cross 3.
20 cross 3. Very good. What will be the hidden?
10 cross 3.
Sorry?
Okay.
No.
20 cross 20.
Very good. Yeah. 20 cross 20. You know why? I'll tell you. So let's take the simple case, right? Let's take the simple case where there'll be just 4 hidden units, right? Now, what that recurrence means is there is a weight that's connecting each neuron in the hidden layer to each other, right? And then so on and so forth. Okay, so if I represent this as a weight matrix, this will be a 4 cross 4 weight matrix, right? Where this will be W11, W22, W33, W44 on the diagonals, right? This is the weight that is for the self, okay, back onto itself. Okay, and then you have W12, W13, W14, right? So these are the weight connections that go from W1 to 2, 3, and 4, and simultaneously to 1, 2, 3, and 2, 4, 3, 1, 3, 2, and 3, 4, and then 4, 1, 4243, right? And that's the reason why this is 4 cross 4. And this is the idea behind recurrence, right? In this, in the recurrence fact comes from this element as well, because you see that information is going within units as well, right? In some sense, right? When you take this and transform it, you are maintaining or spreading information across the hidden layer activations according to this weight matrix. And this weight matrix define the connections between the hidden layer in activations or the hidden layer units here. So for instance, if this weight is 3, then there is a specific type of interaction between the second node and the third node, so that the information from the second node is scaled 3 times when it goes to the third node. And you can see that there is also directionality, that is W24 is different from W42. Right? It can be same too, then it will be a symmetric type of interaction, right? But it can also be different. But these are typically trained through backprop, but it's nothing but the same extension of the simple feed-forward network. Now we have an extra set of weights, which is this weights hidden. Okay. People are on board with this, right? Everyone's on the same page. Okay.
So architecture-wise, it was shown that can go forward.
Yeah, but that was through time, right? I was taking this connection and then putting it forward, right? That's the same thing. If I go back one step, let's take this case. Right? This is again the same thing. This is if this has an activation of 20 cross 1, this is 20 cross 2, right? And then it gives you the next. This is also 20. Okay. It's basically the same thing. Yeah, it's just unwrapped in this case. It is all wrapped here. It just is unwrapped.
And this one allows for the backward part, that is the 4.
Exactly. And this way, the back propagation is easy to visualize, or any sort of training is easy to visualize, because if I tell you about backprop here, then you will not know what's going inside here, right? But now, if I spread it out like this, it becomes easier to grasp what is happening. Okay, cool. All right. So yes, so hopefully people got the logic of how the dimensionality of the weights changes in, or the weights look like in a recurrent neural network. By the way, it does not it's not necessary that there is just one hidden layer. There can be many hidden layers, right? So making this also a deep architecture in some sense, right? So these are deep RNNs, where if you think about it, you have the input sequence that's coming in. There are two hidden layers, hidden layer 1 and hidden layer 2, which have their activation. So let's say if I call this hidden layer 0, I have the activations at time step 0, time step 1, time step 2, right? And there is a weight that's taking me from hidden layer 1 to the next time step of hidden layer 1, which is WHID1, okay? And there is again a transformation from the hidden layer 1 to 2, which is done using, say, WHID1 to 2, for example. And then the hidden layer 2 is also moving across time, right? Now you can imagine that this can now solve a little bit more abstract problems in the sequence, find out more complicated patterns in the sequence, because as deep that you go, the more abstract representations that you can extract from the input. But again, there are issues, because if you have many layers, then the problem of the vanishing gradient, which is often the trouble with a lot of deep networks, vanishing and exploding gradients becomes an issue. But these sorts of extensions to this architecture is also possible, right? Making the architecture deep in some sense. Okay, everyone's cool with this? Because it's just a simple thing. It's just an addition of another layer.
Correct, sir. But you added one more point which is valuable. But how is it making more significant than others, sir?
What addition does it give you in comparison to the previous architecture is what you're asking?
Yes.
So the point is, the reason is that whatever representations that you would form at this level might not be complex enough to extract certain complicated things from the sequence, for instance, right? If there are things that has to be transformed once more in order to say at that level things are a bit more separable across time too, for example, then you would add more layers. Like, why do you add more layers in a feed-forward network? You want to start solving things that are much more nonlinear and complex, right? Like, you want to make sure that at certain level there is some linear separability of the data to do certain predictions. At the same way, there must be in that same analogy there, if we add more layers to this network, we are able to extract more complex patterns or sequences in the data, and that way we'll be able to make better predictions about certain subtle things. That's the idea, right? That's why we want to do this. So that's the point of adding more layers to it. But again, there's computational challenges to doing that. All right. Okay. So if people got the basic logic behind what recurrent neural networks are, what are the different types in which the architecture can be organized, one of the things that we also I also wanted to touch upon is the loss function, right? The loss function typically depends upon the type of problem being solved. That is, what are you trying to do? Let's say if it's a prediction problem, that is based on a sequence of information, you are trying to predict what next is going to come given that particular sequence, then that's a prediction problem, right? So typically you can use a loss, which is mean squared error, or squared error loss can be used, which is half of y hat minus, right? So which is y hat is the network predicted output, y is your original target output, and then you can use this. But if you want to classify the sequence into a multi-class problem, like whether the language is Spanish, French, or any other thing, or Indian languages could also be taken, for instance, then that becomes a classification problem. Then you can use other types of losses like cross entropy. But the idea is basically the same. You are trying to minimize the loss, but this time you are giving it a sequence and then taking the output, seeing what the output is, whether it matches your underlying prediction. If there is a loss there, then you backpropagate the loss through time. And how does that work? We'll have a look at it in the next slide. Right. So we can do backpropagation in RNNs as well, but it's often what is called backpropagation through time. What that means is, as this network is unraveled, the loss that you get, or the change in the loss as a function of your weights, is estimated by backpropagating this error across this network through time. That means, depending upon the length of the sequence, you will go backwards in time even further, right? And if the sequences are short, then you will go for shorter, shorter distances in the past. And the same way as you would do the backprop for a normal feed-forward network is how you would do it for this case as well, right? You will look at the change in the gradient with respect to y, and then updates the w out, and then backpropagate it through that, and then do one layer at a time, right? Like, you would do this, and then this backpropagates here, and then you would do this, and so on and so forth. And this time, this idea of taking the errors through time, although it's a very misleading terminology, right? Time never goes backwards; it's always forwards. But for the sake of the way in which the architecture is organized, you are going backwards through time in some sense, right? And then updating the weights. So this is how the backpropagation would work. But the mathematics and the mechanics is basically the same, right? It does not change from our previous things that we did. But just this time, this is just that it's going across time backward to the start of the sequence. And that's how you update your weights. And once the weights are trained, as we mentioned, these are fixed. These don't change. So if your input sequence change, the weights won't change. It's just the hidden layer activations that will change across time, which will predict your output. And that way, it's very interesting that such a very simple setup can help you do sequence learning. And we'll look at the pros and cons of it, but hopefully everyone's on board with this. Any questions? Just you can unmute yourself and ask me. Okay. All right. Now, there are certain shortcomings of RNNs which we will address with other types of architecture. But any thought where this architecture might have issues? Any sort of intuition? Anybody has some thoughts about that? Where would this likely not work? And why would it not work? I gave you some clue a few slides before, but
it may not work for a very high length sequence.
Long sequences,
Right.
very nice. Exactly. Yeah, that's the point. Yeah. So the RNNs are very sensitive to recent inputs, right? That means that if you imagine that this is going, for a long period of time, and this is a big sequence, what you saw at, say, time step t minus some capital T, right? That might not still be preserved when you come to the output at the time at which you predict. And if information at this time was very relevant for you to make a decision at this time point, that might not get reflected in the hidden layer activations. By the time it comes here, those could have been overwritten in some sense, and that way you would not be able to make the appropriate decisions, right? That's number one, right? So the sensitivity to recent input makes them very insensitive to digital inputs, sort of a corollary of that, right? So the digital inputs do not influence the model, and if the answer that you're looking for is something that depends on a context that's way back in time, then that affects your model and the model performance, right? Another point that I made was this idea of exploding and vanishing gradients, right? So if you can imagine that if you have a very long sequence, the change in the error that you feel here, the gradient, right, that you feel here would be maximal in the initial layers, but then that would shrink, further shrink here, and then further shrink. And then at the earliest levels, you would not even feel the change in the error that you see at the output here. So that way, it's a problem, and it's especially a problem with the recurrent neural networks, is because if you see that these weights, right, these weights do not change across time, right? They remain the same. And often what tricks that you can use in CNNs to prevent this vanishing gradient and exploding gradient problems is you often would take the weights and renormalize them, right? Renormalizing the weights is one form in which weight renormalization is one form in which you can prevent this vanishing and exploding gradient problem. That is, if the weights are too low, right, then you normalize the weights such that it's between some scale. Okay, so but still maintains the relationship across the nodes, but you just are renormalizing them, and that way you can make sure that the weights are still sensitive enough to pick the error from things that are way ahead forward in the network. But you can't renormalize the weights here because the same weight is being used in the previous time step, right? So if you do that, then it will affect what the sequence information is. So you are sort of creating a bias by influencing the weights itself, right? So that is something that you cannot do in a RNN, right? So that's a problem. And so this vanishing and exploding gradient issue has to be solved in some specific way, right? And that's why certain specialized architectures which are extensions of RNNs emerged. Okay. So that, and then there are really good models. RNNs are actually, you can even, with hopefully today evening, you have a tutorial for some feed-forward networks and CNNs. Should have happened last week, but it got postponed. Otherwise, this week we would have done a little bit of RNNs in PyTorch. But you'll see that they are also really good models of replicating, but the recent past, right? If there are, if the dependency is just on the recent past, and when I say recent past, I'll put it in quotes because that depends, right? What is the length of the past? Right? Recent past could be anything, but if the sequences are short enough, then it's really good. It works like a charm. Right? But then when a context information has to be taken from way back in the past, then it becomes a problem. Right? So that's where the extensions of RNN models, especially LSTMs and GRUs, came into the picture. Right? They sort of help overcome these shortcomings. And we'll look at how these are organized in order to understand what they do, what is the logic. They are a little bit complicated. And I would say if you understand the logic, it's good enough. But the real intuition comes when you do this in practice and when you put it to practice. That is, you work with a model. So here we'll discuss the idea and the logic behind it. And I'll try and do my best to explain it to you. But the real intuition would come when you actually do work with them. Okay. But let me go over this. But any questions till now? People are good? Then we can move on looking at these. All right. So let's first look at, before you look at LSTMs, I wanted to introduce you to gated recurrent units, often called GRUs, because they are slightly more complicated than RNNs and a little less complicated than LSTMs. But if you get the idea here, then it's going to be easier to grasp, or at least get the logic of what LSTMs do. Okay. Let's understand GRUs. But before we even go into GRUs, let's understand the idea of a gate. Okay. Because this entire, this GRUs has the word gated or the word gate in it. So what's the idea of a gate? Anybody? What does a gate do?
It's kind of a control.
Limited input.
Right. So it sort of tells you that I'm going to send something, but I'm not going to send some things. Right. Like I'm going to allow some things to pass through. I'm not going to allow certain things to pass through. Right. Now, computationally, you can execute a gate using a sigmoid function. Right. If you think about it, because given the input x, if the x is close to 0 or x is high in some sense, right, you can threshold, or in some sense push the inputs or the outputs of this to either 0 or to 1, right? Yeah. So depends upon the nonlinearity of the sigmoid, but let's say that we can set that. But that way, what this acts as is some form of a gate, right? Like it allows certain things to go through where these becomes 1, then it allows those input part of the input space to go through, and those which are close to 0, it blocks them, right? So in some sense, a sigmoid function can be used as a gate, right? So it lies close to 0 or 1. So in some sense, you are pushing certain things, you are attenuating certain things, right? So if I take this function and weight, right, other inputs with the output of this function, that will allow certain information to pass through and certain information to be blocked. Okay. And that's why this acts as a gate. Okay. So if I take the output of this and I multiply it with, say, something which is important, right, it will make sure that it will retain some of the information where it is allowed to pass through. It will be 1, and those which are close to 0, it will not allow them to be represented anymore. Right? And that's the idea behind gate. And the gated recurrent units is that is that sort of a network architecture where you use this gates to allow information to pass through, or which information to pass through the network. So that's the idea. So how do you represent these GRUs? So let's first take a basic RNN unit. So we saw this, right? This is a basic RNN. Okay. And then I can write the basic RNN equation to be more compact like this, right? So instead of writing it as W hid times HT minus 1 plus W input times XT, I can combine all of them in a single weight, WH, which is a combination of these two things, right? W input and W hidden. And then I can just concatenate my hidden inputs, previous hidden layer outputs, and then current input. Right? So you can do that. So this way, it's a compact representation of what is the hidden layer activation at time t, right? And the tan h is the activation function. Okay. Now, typically, you must have seen papers or sources online where this kind of representation is converted into something like this. Okay, so let's take this to be the unit, this to be the recurrent unit. Okay, now what you are seeing here is that there is an input, and then there's the previous hidden layer outputs combined through the weights WH through a transfer function or an activation function tan h, which gives rise to the next hidden state, right? And you can also extract the output or the predicted output of the network if I take this hidden activation and pass it through some output weights. Okay, got it? Right. So this is how you represent your recurrent neural network, a simple version of it, the basic version. Okay. Now, how do GRUs look? Okay. So ready for this? Now, this is how GRUs look. Okay. So slightly more complicated. Don't feel intimidated by it, but we'll look at every component one by one. But what I would like you to appreciate is that we still have this basic unit here, right? HT plus 1 XT, which goes through the tan h and gives you the next hidden state, right? Yeah. And what we have are certain additional units, right? Which have these gates, right? Because these are sigmoid functions, these are certain gates that gate your input and output in specific way, right? So as to remember some information and forget some information. Right? That's the idea behind the gated recurrent units. Okay, and these are the equations that are representing this particular cell of the recurrent unit. We will look at each of these equations one by one and what exactly they do. All right. Okay, everyone's on board till now? Yes. So let's look at each of these equations one by one and see what they mean, right? What do they actually do? Okay. So before we move on, the idea of GRUs is you want to preserve representations of information over time. That is, you probably want to drop those information that probably are irrelevant, right? You don't care about them, so that information that you do care about is getting preserved across time, right? And that way, what you can do is keep hold of more and more past information, or a longer information about the past, which might not have been possible if you just use a simple recurrent neural network. And how does this do it? We'll have a look at the next slides to understand that. Okay. Everyone on board? Any questions? Okay. All right. Let's move.
One thing.
Yeah.
In this diagram, like gate is the functions, right?
Yeah.
Sigmoid and tangent.
Yeah.
These are the
No. The sigma is the gate. Tan h, I told you, tan h are more. You should think of them as more as activations or representations.
The final activation.
Final activations, yes. The gates would be these. These are the gates.
So this entirely is one node of the network, right?
This is just one, not one node. You can consider it as one cell. Yeah, that means that here you can have multiple nodes, right? Input can be of multiple nodes, hidden states can also be of multiple nodes, and so on, right? But this is one current cell of the network, right? This ht then comes back as ht minus 1 to this. Yes, and you can have multiple of them too. That's fine, right? You have one on top of the other, then that could also be a deep graded recurrent unit, right? But this is one unit of it, one particular how do I put this? If I go back, this is one instance of your recurrent network, which I represent it like this. That's the same here for GRG. Okay, all right.
Sir,
Uh-huh.
we could have used ReLU function as well for gates because
So when I say gates, right, then something has to go through, something has to be zero. Like sigmoids are much more gate-like because they set the higher activations to be a 1, right? Whereas for ReLU, then it'll be it'll be scaled, and you don't want that information there. You just want things to go through or not go through, right? And that way the sigmoid is better as a gate than a ReLU function.
Like a yes.
Sorry?
Like a yes, no. Zero.
Like a yes, no. Yeah, exactly. Yeah. It's not a very hard yes, no. Again, there is a linear part to it, right? But again, this is much better as a gate than other things. Yes.
It's a kind of filter.
Yeah, somewhere intermediate. And also this sort of functions are differentiable, right? So to do a back propagation, it becomes easier. If you use like a very hard step function, then there's a non-linearity at certain
So any
points.
max limit to hold the last layers? I mean, because here we are, skipping the weight. I mean the stage which we don't need, right? So that we can keep the most important stages, right? But there should be some limit. I mean, with the max limit. After
No,
that,
no, no. We'll talk about that. The point is that still these are weights, right? These are weights that are there. These are still trainable weights. That is, you decide or the network decides what to keep and what not to keep depending upon what objective function that it's trying to solve, right?
do we
So
have
at
any
the
max limit?
max limit for what to keep or what not to keep,
Yeah, yes, yes, yes.
that depends on the network, right? That's what I'm trying to say. That depends on the network when you're taking these hidden layers and these weights, right? Depending upon how the hidden layers and the inputs get scaled by these weights, certain information could be dropped, which could be much of the information or a little bit of the information, depends upon how these weights get trained at the end of the day, right? So you do not figure this out, you do not set this by hand, the network figures it out. That's the advantage, right?
So are we using RNN in any case, because this is something we do have the limitation? So I think
As you say that this is slightly better than RNNs because it can hold much more information about the past. But again, this requires a lot of data to train. So there is the flip side to it as well, right? You need more data for such a network to train compared to say a simple RNN, right? So if you don't have too much of data, then there's no point in training a GRU over an RNN. But everything has its
yeah,
trade-off.
it's in the length of the sentences in case of the
Exactly.
text everything,
Right. And how many such
right?
sequences you also have is important, right? As you're training data,
So basically,
that also impacts.
it's all about the token size.
Exactly. Yeah, you're right. Okay, people are good. Okay, perfect. All right, so now let's look at each of these gates, right? Each of these gates, what do they do? So the R is what's called the reset gate. Okay, as the name suggests, it's resetting something. But what is it resetting? Okay, what it's taking is it's taking the input and the previous hidden states, passing it through some weights, and then there is a sigmoid function, right? And if you see this arrow, this is placed before the tanh function, before the thing. I'll tell you where this R implements. But what is the point of this R? The R is intuitive, right? So there's not much going on here. It's just weights. You're taking some weights and then you're passing your previous hidden state and your current input, and then the output is weighting something. What it is weighting, we'll have a look at it in a couple of slides, but it's deciding how much of the past to update. Then comes the update gate. Okay, the update gate, if you see, it is the same formula. There's nothing different about it. It's still taking the past hidden state. It's still taking the current input. Now the weights are different, and where this U acts on is different. Okay. Now what does this do is it decides which items to update in the hidden state. That means when you compute your next hidden state, the update gate tells you how much of the previous hidden state to keep and how much of this new hidden state to add to it.
But sir, it can be go as the input to 10H, right? Hello?
Now you can imagine what's happening there. Now, the information from the previous hidden state is coming in, right? And this reset gate is telling all those hidden states where the R value is 0, those are becoming 0. So those hidden representations you are forgetting or resetting in some sense. Okay. And all those places where R is close to 1, those you are allowing it to pass through to calculate the new information. Okay. So that way you are combining your current input, previous hidden state, but you are weighting the previous hidden state to generate this new candidate hidden state. Right? So this N is not an gate. N is more like an activation or representation. So wherever you see this TANH, that's more about the internal representation of the RNN. Any questions here?
Sir, could you please repeat what is it doing, this new information gate?
So the reset gate, right? So for instance, let's say the hidden state had some representations, correct? Right? That is, it has some series of values, right? From -1 to +1 that you got from the previous step. Wherever this R is 0, right? R is multiplied by HT -1. Wherever this R is 0, those representations are switched off or reset in some way, right? In some sense. And those places where this R is 1, those representations are preserved, right? Now, what decides which representations to preserve? These weights, right? Because these weights are deciding how this R will look like. And when this R influences this HT -1, it then decides which representations to preserve, which representations to reset, right? And that way, what you are doing is you are allowing some information from the past to be forgotten and some new information from the present input to be there in the hidden state activations. And that's how you get your N, which is your new information. Okay.
No. Okay.
Okay. Yeah. So if you understand the logic, it's fine. But as I told you, if you don't put this to practice, if you do not work on a specific problem, it's going to be hard to exactly know what's going on. But if you get the intuition behind it, that's more, I mean, that I would consider that as a win, right? So the fact that this reset influences the previous hidden states to determine which should actually be reset and which should actually be preserved, right? That's the idea. That's the idea of a reset gate. So that's your new information. And then finally, what that takes you to is your final output or the final hidden state, the next hidden state. And that's where your update gate comes into play. Okay. The update gate tells you that this is my previous hidden state, right? Keep some of it. This is my new hidden state. Keep 1 minus that, so that you have a mixture of the previous and the current. Okay, right? So there is a difference between the update gate and the reset gate, because if you see, the reset gate applies even before the TANH happens, right? Before the new information gets computed. So even before it goes through this nonlinear activation function, it resets those information that probably isn't necessary, right? And once the new information gets computed, right, there's a previous information that's preserved. Instead of taking all the new information, right, you take some of the previous information and add to it some of the current or the new information.
Sir, like if we put UT as a 0,
yeah,
then HT become NT, right?
If UT is 0, then it's basically all of the current information that you are taking. But you should realize that UT is not a univariate, it's a vector, right? That is, it's multiplying with each of the hidden states, right? So that means some of the hidden states might be turned off, some of the hidden states might be turned on, it depends, right? And the vice versa will happen in the new information.
So like one thing I want to know, like 1 minus UT, what is representation of this term?
1 minus UT?
Yes.
1 minus UT is nothing but whatever update that you had here, right? You're taking 1 minus that. So you're taking some amount of the previous, right? Depending upon what things to update, right? And you are taking 1 minus that for the new information. So whatever is remaining, you are adding the new information to it. Whatever is going through, you are taking some proportion of the previous thing.
Means whatever you have, that is with P minus 1 and what remaining with NT, right?
NT, yeah. So whatever is new information, you are adding some of that current information to the previous, and that's your new hidden state. So what essentially happens is that the current, it's a weighted sum, right, of the new candidate state and the hidden state. So you are preserving some of the previous and updating some of the current. And this way what happens is you can keep hold of the past for a long period of time, right? Because you're not erasing it altogether, and you are updating it also in such a way that the relevant information about the past is staying there for a long period of time. Now, what is relevant, that the network decides based upon the objective function you are trying to solve, right? So that the network decides, but the mechanics of it decides how long that information will get preserved. Okay, so that's why it helps you work with even longer sequences. All right, people are here with me. Hopefully people are all on the same page. It's a bit complicated, I know, but I guess the logic is clear. The logic is you are first resetting some of the previous information to calculate the new information, and then you are updating the next hidden state based upon the previous and your current information. That's about it. That's what GRUs do. Okay, and this way what happens is that since the relevant information is getting preserved, right, because then it becomes easier to make decisions based upon the past. Although these are slightly more trickier to train and require more data, they do work with longer sequences very well. Okay, people are good, right? Yeah, so I hope people understand this, because next we look at LSTMs, which are more complicated than this. So hopefully this is clear.
Sir, I have a question, but on the back propagation part of this.
Yeah.
So, I mean, when you back propagate the loss, so I can understand like WN getting updated, but and WU be impacted, like how?
Oh yeah, of course, it's the same way, right? In case the U in this case, what would it be? Then the U, okay. So you mean to say again, these are all functions that would be potentially differentiable, right? So you want to differentiate it with respect to WU, right? NT in this case, UT would be what? UT would be G of WU XT HT minus 1, correct? Yeah. So the change, so any change in U is going to change HT, right? And any change in HT is going to change loss, right? So the loss is going to be back propagated, and this way you differentiate it with respect to W, right? WU in this case, and that way you will get the rule for or the update for WU.
Sir, not in terms of mathematics like that I get, but like how does the same, I mean, like three different weights, like how should you, like intuition behind it is
Okay, very good. So that's a good question. So when people started working with this, and it's important to stress this point, right? When people started working with sort of updates to the basic RNN model, which is easier to understand, right? Like people agree with that. They did not wake up one day and then said, okay, if I make this connection, and this happens, so suddenly I am able to do better. No, it was an iterative process, right? People started playing with gates. People started adding one sort of gate to it and seeing how the network performs. People started adding some more information. There is some intuition that you kind of get when you work with such models, right? And this is a result of those iterations and those things that work, that make it into literature or make it into textbooks or whatever it is, right? At the end of the day, which we end up studying in courses, right? But what my point is that this wasn't like an overnight thing where people woke up and thought about, okay, let's just add these gates and then it will suddenly start working. No, right? The point was it was done in an iterative manner where the concept came from the fact that if I have to remember some of the past, I have to forget a little bit about the present. That was the intuition, okay? Because you should think of it like, if there needs to be some space in the memory to keep hold of the past, I cannot just take all of the present information and then assume that the past will remain there, right? I have to forget a little bit about my current stuff so as to retain information about the past. And that's where the intuition comes from. So what if we use gates to decide which information to retain and which information to not retain, right?
But sir, when back propagating the loss, let's say we get a large loss at the end of the output. Now we can update the WN with respect to that loss, but how does the same loss tell us, like, what is the, like, should we update more of U or should we update more
of course it tells you, right? Of course it tells you, right? That's how the dynamics of H is so U is changing H, by the way. You know that, right? That is, you know that WN, a change in the X and H is going to change H of T, which is going to change loss. But a change in U is also going to change H of T, because that's how H is defined, right? H of T is 1 minus U of T. So a change in U is going to change H. And that way you'll know how to change U in order to make sure the H is in such a way that will minimize loss. Right? That's the idea behind it.
This you have to understand U of T, right?
Yeah, that means you need to understand that U of T also affects H of T. And in that some sense, H of T is also getting affected by R of T, because R of T affects N of T.
Yes.
Right?
N of T.
N of T. Or NT, sorry. Right? RT affects NT, and that's why it will affect HT, which will affect loss. And that's how it gets back propagated. So you know that. I hope that was clear.
Yes, sir.
Okay, cool.
Sir, can you describe some more points on the update gate also, because I think that time the network was down.
Okay, of course. Yeah. No, the point was that the update gate, right, tells you, or it helps gate information from the previous hidden state, that is your past. So if you follow this black line, right, this update gate influences that, and it influences whatever new information was updated, right? The new information, right, is weighted by U, and the previous information, weighted by 1 minus U, and the previous information by U. So your current hidden state is a weighted combination of your previous hidden state and the current candidate new state, right? So in that sense, you are preserving some information from the past and also taking some information from the present. This way you are able to hold on to the past for a much longer period of time, and easier to make inferences and predictions about longer sequences.
Yeah. When I say update gate means like second B equation, that ut equals to sigma.
Oh, okay. You mean to say this? Yeah, it's not. It's nothing. So, in fact, there is no difference between RT and UT in terms of what inputs they are taking. Right? It's just the weights are changing, but and where the influence, the hidden layer state changes. Right? So, if you see UT is also taking the previous hidden state current input and then passing it through some weights WU, and then you get your U. Okay, so in essence, there is no difference computationally between them. Numerically, the WR and WU will change because reset gate will decide what parts of the past to reset. Yeah, no need to put them into consideration. Update gates tells you how much of the past and the present to consider. Okay. So that's how they work.
Okay.
And so the black line you mentioned that comes directly.
Yeah.
This one.
Yeah.
What's the purpose of this?
So this is telling you this, right? This is telling you HT times UT. HT minus 1 times UT. So HT minus 1 gets weighted by UT to get you the next hidden state.
HT minus 1 is your past, right, sir?
HT minus 1 is your past hidden state.
You are updating your past.
You are weighting your past with the update gate, and also your current information.
Impacting the output of current.
Impacting the output of your current hidden state. Yes. Okay.
Got it.
Everyone's on board? All right. Perfect. Okay, guys. So hopefully, if that was clear or clear-ish, I would urge you to hold on to your seats because we'll look at what's the time now? 11:10. Oh, I really wanted to finish LSTMs. Guys, can you give me like 10-15 minutes max? We can finish that if people are okay with that. Yeah. Let's look at LSTMs. They are slightly more complicated.
Sir, can we start from next class?
The point is, I understand this is a little bit too much. Okay, we can do that.
But we need time to understand.
Of course. Let's maybe let's stop then. It's a good idea. So I'll just conclude some points about this, and then we can do it in the next class. But we might have to do it on Saturday after the quiz. So we'll do it after the quiz on Saturday.
Sure.
And then on Sunday, because I think Fractal 1 gets over. I might want to take one more class, but that depends, right? To talk to Dr. Pratik as well, but we can do that. But hopefully this was clear, right, for people. Like this is a long sequence of information. So just to summarize, at the end of the day, what we saw in RNNs was a way to understand sequence information, or data structures that have temporal relationships in them, and how to exploit those relationships to make computationally relevant problem solving, be it sequence prediction, sequence classification. And we looked at how RNNs work, how backpropagation through time works, and what are the different ways in which the architecture can be reorganized to give you a specific type of problem to solve. And then we started looking at the limitations of RNNs, why they are best useful in scenarios where there are short sequences and not too long, where you don't have to look too long into the past, right? And then we looked at an extension of the recurrent neural networks, which is the gated recurrent unit, right? So next we'll look at LSTMs next week, right? But just to give you a short preview, this is how it looks like. So brace yourselves for next week. Yeah, we will do some reading about it so we can have a good discussion in class. Okay. All right, guys. Thank you. Any other questions? Then let me know.
Sir,
quiz syllabus.
Yeah, quiz we'll do it till GRUs, guys. Okay. Yeah, but the last parts till you did it now, maybe I won't ask too many questions, and it'll be just like few questions, guys, like 4-5 questions max, right? So you don't have to.
Is it more subjective in nature or objective?
It'll be descriptive, but it'll be very short answers. Yeah, I don't like very long answers to stuff, right? You just have to. It'll be conceptual. It'll test your concepts. Yes.
So yesterday you talked about one paper for
Yeah.
CNN.
Yeah.
And also for
I put it in there so you can access it. So I think let me just go back. The source is in there, I believe. Yeah, there. Yeah, I have it.
So if you can paste it, copy. I mean.
Sure. I mean, you can. I just put the slides up. You can just copy paste this.
Acha, okay. Slides are there. Okay.
Yeah, slides are there. Yeah, slides are there.
Yeah.
I upload the slides generally on the same day in the afternoon or evening, so you can have a look at it. Yes.
Thank you, sir.
Okay, perfect. All right, guys. See you. Have
Thank
a
you,
good
sir.
rest of the Sunday, and then
Thank you, sir.
I'll see you next week. Thank you, guys.
Thank you, sir.
Thank you, sir.
Thank you.